Hello and welcome to the second session of our CFD for HVAC and AEC application workshop by SimScale in collaboration with Rhinos 3D. My name is Milad and I will today again be your host and guide you through the topic of our second session, which will focus on natural ventilation and how you can simulate and predict natural ventilation phenomena inside buildings using CFD. But first things first, and before we start to dive in our today's topic, I would like to make sure that everybody can hear me loud and clearly. And you should know it from yesterday. We are using this tool GoToWebinar, and please click on the raise your hand button in the case you can hear me loud and clearly. Well, looks like everything is working from a technical point of view. All right, so let's start. And first of all, I would like to take a look at our curriculum. And just in the case, if you missed the first session yesterday, you don't need to worry. We will record both sessions and provide you with the recording tomorrow by email. Okay, and to put it in a nutshell again, the idea of this workshop is to introduce interested engineers, designers, and architects into the world of computational fluid dynamics, and participants will learn what are the fundamentals of fluid flow simulation, how they can use it in their AEC project, and the final aim of our workshop is that this workshop will prepare you to get started on your own and help you to gain your first very own hands-on experience with CFD. And this workshop is made out of two sessions. Yesterday, during the first session, we were talking mainly about mechanical ventilation and how you can use CFD flow simulation to predict mechanical ventilation systems. And we talked a little bit about the fundamentals of simulation. So what is the basic idea of simulation? How can it be used and leveraged inside the AEC or HVAC design process? And finally, we went through a real-world example, and together we optimized the smoke and pollution management inside the parking garage. And in contrast, today's session will focus on natural ventilation. So again, we will talk about, let's say, the fundamentals concept of CFD and how CFD can be used to model natural ventilation. In the case you missed yesterday's session, I would recommend you to take a look at the first 20 minutes of the recording from yesterday. Since I will not again talk so much about how simulation can be used, but more about how it can be applied for ventilation projects. And again, we will have a live demo. And together we will analyze and validate a natural ventilation concept for a small shopping mall building. All right. As I mentioned, I don't want to repeat too much from yesterday's sessions. Just a crisp overview, since some people joined for the first time today. So SimScale is a free and web-based simulation platform, which means that our vision is to democratize simulation and make engineering simulation available to all engineers in the world. And the great thing about SimScale is that, first of all, you can access this from ever you want. You just need a web browser and a working internet connection, and everything else is performed in the cloud, including the heavy computations and the storage of your data. And it's really great because there is no need to buy dedicated software or hardware, and basically allows you to get started with CFD from a technical point of view within several minutes. And flexibility is a very important point. And besides the flexibility this web-based approach gives to our users, we also have a very interesting price model, which is basically starting from free, a freemium price model, and which should basically give every engineer the right, let's say, package to use simulation. And finally, SimScale is designed for everyone. So when we designed the SimScale user interface, we really had the requirements of new users and designers in mind. And so SimScale, you can say SimScale is the first simulation tool which was made for designers and architects. Yes, and today we will talk about natural ventilation. Yesterday we talked about mechanical ventilation, but for sure there are some more applications of CFD for the AEC industry. And with SimScale, you can basically perform fluid simulations, structural simulation, and thermodynamical simulations. And especially the fluid flow simulations are not restricted to ventilation at all. And here you can see some examples how our customers and users are leveraging simulation for their AEC project. And this can include, very high performance HVAC systems, like the systems used in airplanes to supply fresh air. But we also have customers using CFD on our platform for building aerodynamics, for example, to estimate forces which are acting on high-rise buildings, or to get an idea about, let's say, the comfort level around larger building complexes. And for sure, you can also use it for different kind of ventilations, and also to improve or optimize different aspects of ventilation, including smoke contamination. We talked about it yesterday, but you can also do thermal comfort analyzers, for example, in larger office rooms, theaters, and so on and so on. And we talked now a little bit about the idea of this workshop and what you will learn. So now let's try to dive into our today's topic and talk about natural ventilation. First of all, so what is natural ventilation? And I know there are a lot of different explanations and definitions for natural ventilation, but in the end, if you want to put in a natural ventilation can be defined as air exchange inside a building, which is taking advantage of physical properties of air. And in practice, usually we're talking about two properties of effect. One is what we call natural convection. So if we have any heat sources inside the building, the air in the near of these sources will heat up, and the density will drop, and therefore it will arise. And this is something, for example, which an effect which is you can also see not only for buildings, but it's also used for cooling electronic devices. And another option where natural vent, or let's say another kind of natural ventilation is caused by external flows. Let's say you have a building with openings to the exterior, then air can travel inside your building, and this can also induce a flow. And the great thing about natural convection is that if we leverage it, it basically comes with no or very low cost for moving the air through the building, since we are leveraging other, let's say, energy sources instead of fans, which are used for forced or mechanical ventilation. And that can be really helpful, especially when it comes to reducing a building's total energy use. And if you think about it, green building is one of the, I would say, most prominent buzzwords nowadays. And especially when it comes to green building or passive house design, natural ventilation can play a key role to make sure that you, on the one hand, you reach your let's say, comfort requirements, but on the other hand, you're able to massively reduce the energy amount which is necessary to run your ventilation system inside the building. And another great aspect of natural convection or natural ventilation is the fact that usually it's more comfortable to us. If you think about the difference between natural ventilation and mechanical ventilation, a good example is the airplane. A lot of people don't like to fly because of the air conditioning inside the plane, which they think makes them sick. And there are some research studies which have proven that, let's say, bad mechanical ventilation can have a negative impact on our health and on our productivity. And besides, let's say, the financial benefits of natural ventilation, another big advantage is that it's less noisy since you don't have any fans, and usually let's say, the airflow is much smoother, and it's easier to realize, let's say, comfort air conditions. But for sure, it also comes with some disadvantages. And first of all, you're really depending on the building's external conditions, especially if you want to use openings between the interior of your building to connect the interior with the exterior. And this includes the design of the building, but also, let's say, how is the terrain structure around your building? How is the wind structure or the actual flow field around your building? This can also include other things like noise and pollution level. Let's say if you have the perfect flow conditions and the design of your building is really good for such natural ventilation design, as long as you have a highway, let's say, on the other side of the road, or if you have some facilities which are like releasing a lot of pollution, this can be a big problem, and it can end in the fact that you are not able to use natural ventilation. And another, let's say, disadvantage or challenge which comes with natural ventilation is the fact that you actually are losing a lot of control about your internal environment. What does it mean? Let's give you an example. If you have a mechanical ventilated building, it's quite easy usually to control the internal environment, and you can adjust, let's say, the air exchange rates, temperature, and all the other stuff very easily by controlling your fans and some other devices. But when it comes to use natural ventilation, you're much more depending on the environment condition, which means you will lose some control. By the way, in the case you have questions, feel free to drop them into our chat window, and I will try to answer them on the fly during the Q&A. I also received some questions via email, and I will also discuss them at the end of our session during the Q&A. All right, so now let's talk about modeling strategies for not for mechanical, but for natural ventilation. First of all, let's start to talk a little bit about the domain modeling and like what is the fundamental idea of natural ventilation simulations. So first of all, we have to understand that basically there are two types of natural ventilation cases which we can simulate. And therefore, you should take a look at the slides and at the sketch of the domain. The first type is natural ventilation, including internal flow only. And in this case, actually, we have our building. So these are, let's say, the walls of our building. We have some obstructions inside, and if we in some optional cases, we can also have openings. And if we do such a simulation, we are basically not considering the effect of the external floor and the interaction between building aerodynamics and natural ventilation. And for some cases, this kind of simulation is everything you need. Especially, for example, if we are talking about passive housing, you usually don't need to consider the interaction with the environment. And if you use this kind of simulation, it's quite similar to the mechanical ventilation modeling strategies we discussed yesterday. The big difference is that, let's say, we don't have any external sources of flow, like we don't have any inlets of fans and we don't have our exhaust. And the flow is induced, let's say, by, and that is very important, by temperature differences. So we're really talking about natural ventilation or natural convection only, and therefore they mandatory require a temperature boundary condition, which means we cannot simulate natural ventilation or the internal flow of a building without having any temperature differences or temperature boundary conditions. And another option is that your simulation can also include external flow or include external flow only. There you have actually additional domain, And then you're not simulating only the, let's say, the volume inside your building, but also, let's say, the fluid domain around your building. And this can be necessary if you really want to validate a natural ventilation concept, which is massively or which should massively leveraging, let's say, the external flow. And for this bounding box around the building, there are some additional requirements regarding the sizing, which I will discuss with you. And this is because you want to make sure there is no interaction, let's say, between these walls, which are separating your control domain with the walls of your building. And another big difference is related to your CAD model. If you want to include the external flow, you also have to make sure that the walls of your model have a defined thickness. Otherwise, it can cause some problems. And for sure, you can also combine both. And like, even if you want combine everything, like that you consider temperature, internal flow, and external flow. Regarding geometry simplification and upload, it's quite similar to what we've discussed yesterday. So in general, you can directly import your Rhino models to the SimScale platform, and for this, you can choose between a native Rhino file reader, you can use a step file import function, or you can import STL files. And each of these file types comes with individual advantages and disadvantages. And from my experience, I would suggest whenever it's possible to go with a step file. And in the case you have a very complex geometry where you want to have full control over the surface resolution, STL file should be the solution of your choice. And for sure, the geometry needs to be clean, so we need to simplify it, make sure it's watertight. And regarding the boundary conditions, they are quite similar to the boundary condition we used for our mechanical ventilation simulation. So we have, again, flow conditions, what we can define, like velocity or pressure boundary conditions for all the patches. And we can also, if we want, add thermal conditions, including temperature, heat generation, and heat transfer on surfaces. All right, now let's take a look at the end-to-end simulation workflow when you want to use Rhino together with SimScale. And this is, again, very similar to what we've discussed yesterday. So first of all, you need to import an actual CAD model of your building. And that's maybe the first difference, because especially when it comes to include the external flow, in this case, we have to make sure that we have a closed volume model. So the walls need to be closed, and as I mentioned, they need to have a defined thickness. And the first step is to import your CAD model to SimScale, and then you can like define a mesh. And the mesh is what you can see on the image here in the middle. And the meshing process means that we are dividing our model into a lot of small hexahedral cells. And later, the algorithms are calculating the flow properties like velocity, temperature, only for the center of each of these elements. And if you can, I think you can also imagine that therefore the size of this element somehow corresponds with the local accuracy of the simulation. So once you've imported your model and you have meshed your model, you can set up the simulation. And again, we have a lot of templates, and you basically just need to follow this tree in the user interface, and it will guide you through every step which is necessary to set up a simulation. And finally, we can post-process and analyze the 3D results in our web browser, or also download them for local post-processing. All right. Now let's take a look at our today's example. And yes, today I would like to perform together with you or show you the results of an external natural ventilation analysis. And for this purpose, we will analyze the natural ventilation process inside this building. This is a small kind of shopping mall, And since this is a green building, the idea was to reduce the energy amount which is needed for ventilation as much as possible. And one idea the architects had was to go with a natural ventilation solution instead of using an air conditioning system or a mechanical ventilation system. And as you can see, it's not a very, very big building, but basically we have the entrance here, which is a large opening, and then on three sides we have windows which are distributed on 3 floors. And what we now want to find out is if there is a potential maybe configuration of open windows and corresponding external conditions which will result in a good working natural ventilation process. And to be able to quantify and to judge about this, again, we will refer to some regulatory standards. And quantifying natural ventilation is not very tough if you have the data. And that's the great thing, that simulation will provide us with that kind of data we will usually never obtain without building a prototype. So, and if we want to measure the performance of natural wind ventilation, there are basically 2 standards which we want to refer to. Both are from ASHRAE, and they are basically used in North America and the Middle East. And the first one is ASHRAE 55 standard, which is about thermal comfort. And this standard says that interior airspeed should not exceed 0.2 meters per second. And in some cases, it's even fine if it goes up to 0.8 meters per second. And the ASHRAE standard 62.1, which is about ventilation, defines the minimum air exchange rate per hour. And for shopping centers, it's required to have 6 up to 10 times of air exchange an hour. And for this, we can basically use 2 metrics which are defined inside this ASHRAE standard. One is the air exchange rate, ACH, which you can calculate by dividing the cross wind flow rate, so the rate of flow which is like going inside the building through the volume of the building. And this cross wind flow rate needs to be calculated based on resistant and pressure forces and cross-section of your building and the entrance. And we will now, first of all, set up a simulation which will cover this effect of natural ventilation. And then we try to apply this criteria and to use the criteria together with the simulation to understand if natural ventilation is possible and where we might find some optimization potential. All right, so again, this is our building. And what we'll do right now, we will basically set up a series of simulations where this building is inside a surrounding domain. And then we will test different configurations of this building where we will open and close with some of the windows. And then we'll take a look how this will impact our air exchange rate as well as the crosswind flow. All right, so, and I have prepared something. So this is a SimScale platform, and as you can see, everything I'm doing here is inside my web browser. And now I'm going to open this project I've prepared, and we will provide you with the project we show you after the session. And so this is this SimScale project. Everything I do right now, it's working natively in the web browser in 3D, and you will never have data loss or any IT problems like that using this cloud-based platform. So as I showed you last time, you can easily upload geometries, your CAD models, and you can choose between a wide range of different file types we are supporting, including STEP, IGES, and STL, but also some, let's say, very relevant native file formats like SolidWorks, Rhino, and Autodesk. And Rhino was actually the first native file format we've implemented, and which is also massively used by our users. Once you've uploaded your geometry, for sure you can interact all the time with your geometry. You can, like, for example, hide parts of the model to take a look inside. And here you can, like, really see that there are a lot of details which are inside the model. And you can also see that this model really is a volume model, and that the walls have a volume and a thickness. Let's hide the floor. And then you can see, like, it's a complex model including a lot of objects inside. Right, and the next step is to set up the mesh. This is quite straightforward. You just need to choose the mesh application. You can basically use the automatic meshing tool, but also manually manipulate the density of the grid. And the great thing is, once you have defined one mesh, you can easily copy it, change the base geometry here, and with one or two clicks, like, you have a new mesh operation, which makes it very easy to run larger studies with a lot of different configurations. Yes, and regarding the mesh, let's take a look, because as I mentioned, it's very important to have the right bounding box dimensions to make sure these walls are not interacting with the flow inside the building. And we recommend to use 3 lengths in front of the building, 4 lengths in streamline direction, and 5 times the height, and the for having a large box and to avoid any interaction. Because if you make this box, you should not forget, at the end of the day, we will define, for example, here an inlet, so the air will enter the domain here. And if the distance is too small, we will have a blockage effect by the building. And this is something you maybe also heard about when it comes to wind tunnel testing. And inside our control domain, we defined also a refinement region, which means that this region, the linear region around the building, will be resolved and calculated with a very high precision. And just because, some people ask a little bit more about this meshing, as I mentioned, meshing is very important, because meshing in the end defines where you will use which accuracy for calculating simulation result. And a level means that we will double the resolution. So we have around, in this box, we have one refinement level, but we are increasing the refinement level on the geometry up to level 6, which means we have a grid size of 2.5 centimeters, which is super fine. And that's a great thing. It's cloud-based, and therefore you don't need to worry about hardware requirements or about, let's say, if your simulation is very compute intensive or not. And this is how the final mesh looks like. And it contains over 5 million volumes, which means we are calculating at 5 million points pressure, velocity, and temperature for the air. And here you can see some details. So this image, for example, is like showing how we refined the mesh in the near of the building. And here really the rule is you need to make the mesh fine wherever you're interested in the result and wherever you expect to have high gradients and high changes. And that's also why I refined the mesh. And this kind of refinement is done, by the way, automatically, why we have refined the edges, because there we will have a lot of interaction between the flow and the building. And so we increase the resolution, or you can see inside the building where we increase the resolution also for small objects. All right, so this is the mesh in the 3D viewer. And at any time, you can easily interact. You can hide parts of the model. You can take a look at the 3D model. Okay, the next step is setting up the actual simulation. And again, Actually, you just need to design one simulation that you can easily copy it, and you will be guided through that process. So at the beginning, you have to choose the analysis type. And this is from a physical perspective. So in our case, it's fluid dynamic incompressible, and then you can even see some examples. And then usually what you have to define is the mesh you want to use for your simulation. Here, the material, in our case, it's air, and we applied this material model to the whole domain. And the great thing is you just need to specify a material by providing us with, I've got logged out automatically. This is due to security because I think I was logged in for a very long time. So let me try to log in again. And you know, that's really the great thing because nothing is lost. And yes, as I mentioned, you can define a material based on the viscosity and the density. We also have a library which you can access to import material properties. And then usually you just need to define boundary conditions. And in our case, it's also quite straightforward. But let's go through the boundary conditions step by step and you will see what I mean. So I will change the presentation to surfaces only, which will make it easier to see actually how the patch structure is looking like. And in the end, like we defined inlet, outlet, but first things first, let's just wait until everything is loaded. And don't worry, if it's the first time you're like opening the model, it can take, I don't know, 20, 30 seconds, to prepare and load or cache all the data. But then everything is running fast and smoothly. And I see we have some questions, and I would like to answer some of them right now because they're related to the demo. And Jade reached out to me yesterday, sent me a nice email, including a lot of questions, which I would like to discuss with you. And his first question was that he saw the demo was all in 3D, 2D. And that's not 100% true, Jade. The simulation actually was in 3D, but during the post-processing, I was analyzing only what is happening inside a normal plane to the floor. And for sure, you can also, since it's a 3D simulation, you can also simulate 3D effects. And actually, I would say that's what all our customers are doing, running this 3D simulation. And since you're interested in floor grills, I think we already have customers using SimScale for that, and also some related tutorials and customer studies. So I would suggest to reach out to my colleagues, or I can forward your inquiry to my colleagues and they can provide you with some material. Then another question which was asked a lot of time, like which file formats we support. And basically, first of all, we support in theory every CAD model, which is a BREREP or facet model, as long as you can export it to STEP or IHS. And this allows us also to import CAD models from CAD tools where we don't have a native import so far. Like CATIA is not a problem, Alpine is not a problem. You can import all the other tools. And this includes also like PDMS tools for plant design and other stuff. And also something a lot of people asked is what happens with your data. So as long as you're using a private account, your data is like private to you, which means that nobody else can access this without your permission. And this includes even the SimScale support. So if you want us to take a look at your project, you have to explicitly share it with us. And therefore, you don't need to worry. You will keep all the rights on your files and your IP. And in the case you're using our free community account, you just agree that the simulations are public available for other users. All right, so we will continue with the other questions in a couple of minutes, don't worry. So in the meantime, everything is loaded. And now let's go to the boundary conditions and change. So first of all, here on this side, we have our inlet, and here the air is entering this domain with 5 meters per second. Then we have the outlet on the other side. And by the way, this is really important. For sure, you need to know the, let's say, average magnitude and orientation of the wind in the area where you're building the building. And then we also have for this side walls, so-called slip walls. And we use this special kind of walls to make sure that we have no interaction with the flow field. And for solid objects, we added is also a own boundary condition. All right, and then we just created a simulation run, added some result control items to calculate the forces and moments on the building, and then we just started the simulation. It nearly took 2 hours and was running on 32 processors at the same time. So if you would run the simulation on a local computer, it would take 36 times longer. Yes, and once this is finished, you can directly access the simulation results in 3D in your web browser. You can interactively post-process them. And since I got a related question also by Bargraph, you can for sure export the solution files, download them, and then you can import them to whatever your tool you want to use, including PeerReview and other free tools, but also commercial post-processing tools like Nsight or Answer CFD Post. All right. Okay. And then there are some other questions by Jade. For example, he wants to know, say in a room of a building, a mechanical fan is exhausting toxic fumes. In the same room, a fresh air inlet is also located. This CFD will also tell me if toxic fume will lead back to the fresh air inlet. For sure, Jade. The great thing about CFD, it will tell you everything because it gives you actually a very precise picture of what is happening on a physical perspective inside your flow field. All right, and now let's go back to my presentation. And yeah, as I mentioned, you can like post-process the results in your web browser. And now I've prepared some result visualizations to discuss the insights the simulation gives to us. And let's first of all start with the thermal comfort, and this is very much related to wind speed inside the building. And this on the slide you can see 6 different thresholds of flow velocity for the configuration where all windows are opened. And if we want to fully comply with HVAC 55 standard, this, let me try to mark them, this for thresholds should be empty, because that would mean that everywhere in this room the wind speed is below 0.8 meter per second. Now let's try to understand in this configuration what is happening. So first of all, on the one hand, we see there is a large threshold or large volume where the wind speed is really perfect. But what we can also see is that this threshold is mainly in the near of the walls. And as more I go like in the the center of this building, the wind speed is increasing. Like it's like a little bit like this, you know, those Russian mamushkas, and it's like an onion a little bit. So the very outer layer, it's like fine. As more we go inside, we can see the wind speed is increasing, and actually we have large thresholds, like this whole part here, where we have really high wind speeds. And another thing, let's say another very interesting information we can obtain from this is how much air is going through which window. For example, if you take a look at these upper windows, it's obvious that there just a low mass flux is coming into or getting outside the building, which is obvious due to the blue color of this area. It's this is really blue, and so like all the airspeed here is somewhere around 0.8 meter per second, while for this large opening and some of the windows on that side, on the second and third floor, we have much more wind going inside and out. Now we can compare different configurations. So this is a configuration where only the windows on the second floor are opened. And you can see like basically it reduced the problem a little bit. So overall, opening only windows in the second window will decrease the size of the threshold where we have high wind speed, but still it's too large. And also what you can see now is that, and this is something which was really interesting for me, that before, when all windows were opening, it seems like the interaction between the windows was creating some disturbance. And now where only the second floor is opening, like all the holes on, let's say, the left side, all the windows on this side are used for exchange, while the windows on that side are still not included to this air exchange process. And you should keep in mind the air is coming from that direction. So, and this is also something you have to understand. The building itself is generating an external flow field. For example, what is happening is that behind the building, usually you have wake and a pressure drop. And therefore, the windows on this wake side, the low pressure side, will be able to more to help you more with natural ventilation than other windows. And we can continue this study and now take a look on a configuration where only the windows here and the first floor are opened. And you can see as more windows I close, as smaller becomes my threshold of, let's say, high speed air. But still, we have areas which very uncomfortable wind situations. And if I only open the ground window, you can see that this is really the first massive change we have to the flow field, because now, like basically only in the ground floor, we have problematic wind conditions. And at the second and third floor, it's perfect. So maybe this could be a first hint. So we won't be able, obviously, to ventilate all rooms just by using natural ventilation. But some configurations like this are more promising. Still, we have this very uncomfortable areas. And if we close all windows and just go with this one central opening, it's basically very good. So the wind speed is fine everywhere. But if we now calculate the wind exchange rates, and especially the air exchange rate and the cross wind flow rate, based on the simulations, it seems like yes, we will struggle a little bit, because if you remember, only all this from these configurations, if you take a look at, the Q seems to be okay. So the cross wind flow rate, but if you take a look at the air exchange rate, it's much too low for all cases. Yeah, now let's wrap up. So what we have learned. That first of all, for wind can massively impact your ventilation, and that it's basically, yes, an interaction between your external flow field and your internal flow field. And the big trade-off we have is that if we open windows, it will increase your air exchange rate, but on the other hand, it can cause discomfort, or let's say non-optimal wind speeds. And in the end of the day, we need to solve this trade-off somehow. And it came out that opening windows is not really straightforward, and that going only with a central opening could be a solution. But this will create debris inside the building, and actually based on this, what I would suggest is to go with a solution where you don't open at all the windows. Try to reduce the discomfort at the ground level by using obstacles. And in the worst case, you can come up with a design solution where the second and third floor are ventilated naturally, and for the ground floor you use maybe some fans. All right, thank you very much. I hope you enjoyed also the second session. And if you want to get started on your own, just go on simscale.com. You can directly create your own free account in 1 or 2 minutes, and then you can directly test it on your own, or you can also schedule a free individual demo with our engineering team on our website. Yes, tomorrow I will send you an email which will include links to the recording of the 2 sessions, some other helpful resources like as public projects I used for the demos, which you can import to your own workbench very quickly, and some other useful resources and materials. I hope you enjoyed our today's webinar, and in the case you have some questions which were not answered today, now it's time to ask them. Okay, and I think Jade asked if there is any info that would tell us what the loss factor is for the opening. And yes, Jade, I think I showed you how I calculated this. So I basically just created a spreadsheet and entered the force values I obtained from my simulation. So this is possible. And yes. And Bhav wants to know if the ASHRAE code data and tables are input in SimScale. Not really, it depends. Usually you get some of your boundary conditions from the ASHRAE standards or the other codes, and then you use the simulation result as the input for the standard calculation. But there are a lot of different possibilities. You can use them together with hand and AND, but you can also use simulation sometimes as alternative. All right, it seems like there are no more questions. If you forgot about something, you can reach out to me by email. And you can see my email address at mmurphy@simscale.com. Thank you very much. It was a big pleasure to be your host and your trainer, and I hope to see you soon. Have a nice week, and yes, bye.